Hello and welcome to today's Explainer. Have you ever opened up a dense chemistry PDF, taken one look at that literal alphabet soup of formulas, and felt like you were trying to read an entirely different language? If you have, you are definitely not alone. In fact, if you're staring at your study guide right this second thinking, I don't understand anything, please help me learn everything in this PDF, you are exactly in the right place. Chemical equilibrium is notorious for being an intimidating topic. It is packed with abstract concepts, constantly shifting variables, and, yeah, some complex math. So it's completely valid to feel frustrated when you're looking at it for the first time. But hey, here is the really good news. Don't worry, we're going to master this together. I'm going to act as your personal guide through this material. We're going to take those overwhelming blocks of text and formulas from the guide and break them down into simple, logical building blocks. By the end of this explainer, you'll see that it's actually just a series of very manageable puzzles. To get there, we are going to follow a 6-step roadmap. What is chemical equilibrium? Understanding the equilibrium constant, Le Chatelier's principle explained, the role of catalysts, mastering ice tables, and finally, practice makes perfect. Section 1. What is chemical equilibrium? All right, let's strip away the scientific jargon and look at our very first building block. According to our guide, chemical equilibrium happens in a reversible reaction when the rate of the forward reaction perfectly equals the rate of the backward reaction. Think of it kind of like a two-way bridge connecting two busy cities. If the exact same number of cars are driving east as are driving west, and they're going at the exact same speed, well, the total number of cars in each city never actually changes, even though there's constant movement. That, in a nutshell, is equilibrium. Now, notice the closed dome over the bridge. That brilliantly illustrates that equilibrium only exists in a closed system, meaning no cars can randomly drive off a cliff or enter from a side road. Crucially, this is a dynamic process, not a static one. The reaction hasn't stopped, it's just perfectly balanced. Because the forward and reverse rates are equal, the concentrations of the reactants and products remain constant over time. And it really doesn't matter which city you start in, because equilibrium can be approached from either direction. Section 2. Understanding the equilibrium constant. So, now that we've got the concept down, we actually need a way to measure this balance using Kc, which is basically our reaction scorecard. The formula for Kc is simply the concentration of the products divided by the concentration of the reactants. So, if your Kc is greater than 1, the math tells us the products are favored. They're winning the chemical tug-of-war. If Kc is less than 1, the reactants are favored. And if Kc is exactly 1, well, neither side is strongly favored. It's a perfectly even match. Section 3. Le Chatelier's principle explained. This principle is essentially the universe's way of maintaining balance. If you push the system, it pushes back. Let's look at the exact cause and effect rules for these disturbances. If you increase the concentration of a substance, the system shifts away from it to use it up. If you increase the pressure, it shifts to the side with fewer gas molecules to relieve that pressure. And if you crank up the heat by increasing the temperature, it favors the endothermic direction, which is the side that absorbs that extra heat. It's pure, elegant logic. So, the absolutely crucial point is knowing how to apply this. As we look at the structure of the essential formulas and their meanings from the source, keeping these relationships straight is key. Let's see how this all builds by tackling a real-world example of a pressure shift straight out of the text. Okay, let's look at the reaction creating ammonia. 1 nitrogen gas molecule plus 3 hydrogen gas molecules forms 2 ammonia molecules. Let's treat it like a simple puzzle. Step 1, count the left side. 1 plus 3 equals 4 gas molecules. Step 2, count the right side. We just have the 2 ammonia molecules there. Step 3, we know from Le Chatelier that increasing pressure favors the side with fewer molecules. Therefore, step 4, the equilibrium shifts to the right and more ammonia is produced. See? You literally just successfully decoded chemical behavior. Section 4. The role of catalysts. Now, when you're trying to understand everything in this PDF, this right here is a trap so many people fall into. A catalyst is often thought of as this magic wand that forces a reaction to make more product. But in reality, catalysts speed up both the forward and reverse reactions equally. They basically act as an accelerator for both directions of our two-way bridge. And because they accelerate both sides identically, they do not change the final equilibrium position or that Kc scorecard we talked about earlier. They just help you reach that state of balance a lot faster. Section 5. Mastering ice tables. If you have been absolutely dreading the math, let me just reframe this for you right now. The ICE table is not a torture device, it is actually a foolproof cheat sheet.
Let's break down this grid logically using the guide's hydrogen and iodine reaction. ICE is just an acronym. I stands for initial concentration, what you start with right before the reaction kicks off. C is for change, how much of the reactants are consumed, marked with a minus sign, and how much product is formed, marked with a plus sign. And E is for equilibrium, the final amount, which is simply the initial row combined with the change row. You're just keeping a neat budget of your molecules.
Once your ICE table is all filled out, finding the equilibrium constant is literally just a matter of following a recipe. Step 1, you identify those final values down in the E row. Step 2, you write out your Kc expression, and remember, that's just products over reactants. And step 3, you plug those E row values straight into your formula and calculate. And when you do that accurately, like the guide demonstrates in its first worked example with ammonia, where we put 1.20 squared over 0.50 times 0.60 cubed, you get a really beautiful, clean result. In that specific example from the text, the math neatly distills down to exactly 13.33, which just goes to prove that no matter how complex the formula looks initially, if you just follow the systematic steps, the math is entirely conquerable. Section 6, Practice Makes Perfect. Okay, so we've decoded the concepts, we've walked through the rules, and we've totally demystified those ICE tables. Now let's do a quick pop quiz to prove to you just how much knowledge you've absorbed in these last few minutes. Here's a question straight from the practice section of the PDF. What happens to an exothermic reaction if the temperature increases? Think back to the universe wanting balance. Think back to Le Chatelier's principle. If we add heat to a system, where does it go? That's exactly right. It shifts toward the endothermic direction. The system always wants to oppose the disturbance, so it shifts to the side that will absorb that extra heat. If you got that right, or even if you just vaguely remembered the rule of opposites, you are successfully understanding chemical shifts. We've gone from looking at an incredibly intimidating document to breaking down definitions, scorecards, and ICE table bookkeeping. Remember, you have the exact tools you need to tackle the rest of this guide now. But before you do, just think about this. Every single cell in your body right now is relying on these exact principles to maintain biological equilibrium. If Le Chatelier's principle didn't exist, neither would we. So the next time you take a deep breath, ask yourself, which way is your internal system shifting? Happy learning.